So welcome back to the second part B of the lecture. I will share screen like this, and we will continue from here. All right, perfect. So in part A, we talked about a simple algorithm for the detection of outbreaks. We looked at some of the statistical aspects, but of course, we see some shortcomings if you have to put these type of algorithms into operation. We already sort of discussed a bit about the low number of reported cases. So in what I showed was the response was a continuous random variable, and I assume normal distribution for it. And you saw for the Salmonella Newport, for example, that case numbers per week were between 0 and 5. So the normal distribution is not necessarily a good approximation in this case. And of course, that's also going to hamper with your coverage probability and the number of false alarms that you're going to get. So you might want to take into account that you have a discrete phenomena and also sort of count distributions. You already saw in the mortality data that you have strong seasonality. For example, we had here we saw the weekly the yearly pattern in the mortality. So this is also something which I touched upon but didn't say much about. One issue, and this became obvious for the COVID data also, that you don't have often no denominator data, how many tests were actually conducted, and so how many were negative in that sense, or how many were done altogether, is not always recorded. For COVID, it started being recorded, but in the beginning, for example, you didn't, at least in Germany, you didn't have the negative, only the positive cases. And of course, if you increase the tests while monitoring disease, you will have an increase in the number of cases that you will detect. And the next question is, why did you increase the number of tests? Was that because you had many positive cases, and so on and so on? On the reporting is that not every case is not every case is necessarily reported in your database. For example, for COVID, there might be people with light symptoms which never know that or never realize that they actually had COVID. We talked about sort of stuff like reporting delays. We already have addressed that such data in real time can be subject to. And then sometimes you even have problems that cases are not actually attributed to the right categories, that you are not sure, is this really a COVID case or not, depending on the case definition. And that might change over time. And then, of course, you have an increase, and so on. Maybe also one is the presence of past outbreaks. So you in the past have outbreaks. And of course, if you use that in a baseline, that's going to inflate it. And so on. These are just some aspects which are worth looking at, and I just want to talk about one which at least is very similar to what I've shown, but uses the count data distribution. It's such a popular algorithm if you have to use something like that, because it's really sort of like one size fits them all for diseases which have low count number to high count number and so on. So the idea, and this is the so-called Farrington algorithms, this idea is that you have a time series like, for example, and that's the one I think I'll be looking at. It will be this one here. You have the time series, and you have to score or classify a particular time point, and that would be the time point. This is the number of cases. Fortunately, time now is in time points since day 0, which was the first week in 2000, I think. And what you do is then, in order to avoid that the seasonality where you have high or low number in between contaminates your analysis, is that you go back 1 year, take a number of weeks to the left. Here it is 4 weeks to the left, 4 weeks to the right, and includes the week itself. And then you take altogether 5 years back in time. This is the observation from 1 year, 2 years, 3 years, 4 years, 5 years. And then you have to formulate some kind of statistical model. And now we see already these are not going to be IID observation, because you can see there's a trend going down. So they're definitely they might be independent given the model. That's even questionable, but let's say that that's the case. But they are not from the same distribution, because the mean definitely is going to be is lower. So how can we actually come up with a model for this? And that is again a sort of a question of going into the direction of regression modeling. So what we will use is a Poisson generalized linear model, and we will use a particular version of it in overdispersed model. So we have additional variance, but you can think of this just as being a Poisson model. And what we're gonna, what we already discussed, what you're gonna do is you're gonna model the expectation of an observation y of t. And you say that's going to be mu of t, and mu of t you're going to say has a structure. It's not just an intercept, that would be that they have all the common value, but it's something which there's also a trend, beta times t. So this is something which takes into account that things can go up or go down over time. The variance would be typically y of t, variance of y of t would be equal to mu of t if you have a simple Poisson model, but in order to allow for additional variance, there's this over-dispersed version where you say that it's going to be phi times a mu of t, and likely phi is going to be bigger than 1, but it could also be smaller than 1. So you're going to take into the count data nature, but here for these data, 300 to 400 cases, it looks very much like maybe the normal distribution in that case is an okay choice. But I'm using this for illustration now. We have here, this is our observation, the black one, and we're going to do the same thing which we did with the normal. We're going to use the Poisson GLM, the overdispersed Poisson GLM, to compute prediction interval. Here it's two-sided, but what we're really going to be interested in is the upper limit of this. And if the observation is outside the prediction limit, then we're going to flag this as an aberration, or say something is unusual. So for the GLM, we can, in very similar terms as before, use that we can formulate a prediction interval for a new observation. We will use again here we will use the plug-in version. So it will be a mean plus whatever we want as limit of the one-sided prediction interval, and then the standard deviation of the ys minus its expectation, right? So this is the plug-in version of the prediction interval, because in this case here it's not possible to compute directly what is the observation. Of course, what is the variance in a closed formula for the distribution of the variance in this case. So we're simply gonna use here the z distribution. The z is sort of the standard normal. And please note that here the mu s hat is, in this case here now, contains, it's not just the expectation of all the observation that we'll have, but we will have here, and this is something which will follow from our model, because we have a model for, so that's mu t hat for the time point s, which is the one which we want to classify. So that's basically, in a nutshell, it is more or less the same that you already saw, except that these are a bit more difficult to compute. You can look into there are functions to do this for you, and you could also compute it manually. That's not difficult. And then you will have all kind of refinements, which is beyond the scope of this course to talk about. But what we can do is we can not compute this here prediction interval directly on the observational scale, which is here the mu-s, but we can take a transform scale. So you can, for example, take a square root transform of your data first, and then you, on that transform scale, compute a plug-in normal based prediction interval, and then you transform that back. Gives it typically, for example, a square root gives a bit of better approximation, a better coverage often of such a prediction interval, because the variance is equal to the mean in the typical setting, and the square root sort of shrinks the variance. But since you have an over-dispersed model, that's maybe not so big an issue. But the another advantage of taking the square root transform is also that you ensure that you're just going to look at positive values also, and because here this, of course, here if you take the plus and the minus, then the minus could go in the negative direction, but here you would typically stay in the positive part. So the question is how much you gain for such transformations, but if you're in the small count setting, I think you can gain a bit. But it's not the biggest thing. What was also nice is that it has an automatic detection of previous values which were unusually high, which were flagged as outbreaks, and it does a reweighting of these. So it has a sort of a 2 times fitting. First it fits, then it looks if some of the values in the baseline are unusually high, then it downweights these, and then it fits again. And there's also something which that it shouldn't sound an alarm if there's like really 0, 0, 0, 0, and then you have 1, 2 cases. And maybe this is sort of like really beyond the sort of the scope of statistics, but this is sort of like it's still not relevant, and you're gonna simply specify a threshold for how many cases you want before you sound an alarm. It's not very deep mathematics, but it is sort of like one reason that this algorithm actually became quite popular, because it was developed for the UK, what back was then and now is called Public Health England, to monitor their laboratory-based surveillance at that time, 1996, which is also quite some years ago. So just to sort of show here the age group of 75 to 84 years. So actually it's this time series here where the seasonality is maybe a bit less clear, but what you see here is that you would have, for example, a seasonal pattern, and you can still take that into account by having these same week indicators, sort of that you use as baseline here, values from the past. And what you see, and please interpret these plots correctly. So what is done is here, the first week of 2007 is that you use all the previous information, and then you do your upper threshold, which, and then you compute this. And so this is sort of like, what is the number? This is the black line, is number needed before alarm. So this is here the quantile which I'm plotting, or 1 plus the value, because it had to be bigger than this quantile. So this is what is shown here. So for example, here that would be that you have all data available until the second week of 2007. So this one here is also now included in the baseline computation, if that is so, and so on and so on. But what is important is you can never look, and the plot suggests of a bit differently, but it's important to realize that you can never, when you have to decide here, is this an alarm or not, you can only look back in time and you cannot look ahead. And for example, this one here is actually, and that's the triangle indicating that this was because the observation was higher than the threshold. This observation was actually classified to be as an alarm at that point. So this is here around the change of the year, where you usually have a bit of higher case counts, but apparently in the subsequent year here, 2009, you cannot see the 2009 start. It's just 2008, but it's not similar high there. So here there was maybe a bit of unusual activity. Maybe it was influenza related, and what the idea would be, of course, that you want to react on something like that. Of course, like with COVID, there's no need to react, because everybody is aware there's a new disease. There are quite many, but for example, with heat spells or with unknown causes or disease which is undetected, you start to look at such things. And of course, this was also something, and as I showed you the Euro moment, something they started looking for, because they maybe were afraid that they were just not detecting the right cases. Is our mortality already increasing? And in some countries, that's actually when they started to realize this is a problem, because for every person which actually died, there were maybe like 1,000 cases of COVID, which in the very initial phases were not actually detected. So this is one thing where they also wanted to use this as a monitoring. Of course, this is for COVID, it's very late in the process, but it's also, and as you saw that, as a computation of how many additional people were affected by the disease. So this is excess mortality computation. Here, this is the Z values is simply mu-s observation minus mu-s divided by the standard deviation. That's the Z score. So this is simply here the z-score in the Farrington algorithm. And let me see if I can write this here this time. Nope. Here, annotate. So we have here the z-score, which I didn't plot, right? But I can simply write it here, z-score. That's simply here the observation, and I will call that ys minus the mus, which is in our case the estimated, and divided by the variance of this. And as long as you can calculate these, and these follow from GLN output, that's the z-score that you saw on these plots from the Euromomo project, right? So if it's far out, then the z-score is high, and you had really some incredibly high z-scores. Again, here you of course need to be careful with the variance, and because there you have this over dispersion also part of it. And I'm not sure the Euromomo project actually used if it uses a dispersion parameter, because I was quite surprised to see that some of the z values are of the range of 40. All right, so imagine, and you have a standard normal distribution, and you say you observe the value of 40. That's really, really unusual quanta, and doesn't fit completely to that. I think mortality was about double of a usual week for some weeks, which is sort of really bad. But 40, I'm okay. Well, I think it gives a general direction. That's for sure. Okay, let me clear this and close this. Right, then we can move on. Yes. So this was just sort of like, okay, I think I brought this here just to show that you can sort of do these things, extending the simple Gaussian framework, where you can have generalized linear model to get the trend modeled more correctly. And of course, you can also not just have linear trend, you can have something more sophisticated there. And you can also have corrections and so on. And if you want to see how this is sort of really done for data, then you can also just look at the code of the lecture notes to see how this is working. I mean, why I wanted to show this is there's another reason for this, is because this Farrington algorithm with some of the modification is actually what is the backbone of the automated outbreak detection algorithm in Germany, but even also in Sweden, actually. So there's a system running in Sweden. I think it still is running. I think it's called CASE, which uses the algorithm of Farrington as part of looking at individual time series. So what we, and this is based on some work by Patty Farrington, the algorithm, but sort of what we provided and what is used in Sweden is the implementation in R to do this. And we since also extended this based also again on work by Patty Farrington, when we did some modifications to get it adapted to the needs we had for the German system. So maybe just sort of like to show you, this is not sort of like purely something you can sort of nice from a mathematical point of view. Here you go really in the direction of that you have a high volume of data, because you get weekly data. Of course, looking at such a time series as I did here in the beginning of the motivational example here, like this, I mean, that you don't really need statistical methods for, but start to imagine that this is Salmonella. Newport is one of 3,000 zerovars that you can have for Salmonella. So somebody would have to look at 3,000 time series. You have a week to do it, because then the new data arrive, but Salmonella is not the only disease which is monitored, or it's mandatory to report. I think in Germany it's about 90 diseases which are reported, and some of them again have zerovars. And then you can start to think about, maybe there's also a geographical component, or maybe I just want to look at particular age groups, or maybe I want to look at particular combinations of this, right? And then you start to sort of really realize that, I mean, looking at each time series by hand is probably doable. You might need some guidance onto what is unusual or not, but looking at 30,000 to 100,000 time series in a week, that's not going to be a lot of fun. And of course, that's where you want to you want a computer system to do that. And that is sort of part we do. Actually, the monitoring happens very much on individual time series, and then there's some mechanism for gathering. And that's what I want to talk about. And if you are interested in details in how you actually get such a sort of, it's not rocket science, I would say, algorithm, but you get it placed into a system in a public health institution where people are actually going to use it and they're going to depend on it. What are the steps that you need to do? So this is really going more in the direction of IT, but modern data science, I would say this is the way you have to go. You can also label it with a more sort of buzzwordy, like that you're going to do machine learning here on these data, and you're going to build a support system. We're not going to automate the outbreak detection, but we can take some of the hard work off the shoulders of, for example, epidemiologists. So this is just sort of like, here's the publication where we describe that, how we approach that from a computer science perspective. But the interesting is also, of course, how did we do the signal detection? That's what is interesting for this course. So there we actually, very much in discussion with the epidemiologist, we realized that there are two parts they want. They want something automatic report once a week, which sort of gives them a summary of what's happening, and this is something you can study. But once they started to investigate outbreaks or alarms, then they wanted actually to have something interactive where they can work with the data directly, maybe change a bit, have a bit of age strata added, see if it's still an alarm or if it's not. So here they wanted sort of like an, we call that a dynamic component. And here we have sort of the signal detection report component, which runs once a week. So here it's interesting. Here we have our big SQL database with all the case reports for the 88 reporting categories, which there are. And again, then you store, some of them have zero-var information, so you can do all kinds of strata for that. And here's the tricky component is, so sort of what's the statistical algorithm to use. And then what we decided is then that we're actually going to store all these results, all the alarms in a database, and then we even process these further with additional methods. And at the end, and that was sort of like really the most valuable output of it, was not the alarm itself, but sort of like they have a report which is sort of like not based on manual labor that you have to sort of find all the information yourself. You have to sort of, it's generated for you, and you can look at it and you can share it with somebody else. And you can also have a quantitative evidence base to support some of the gut feeling they have. They think that maybe something is unusual there, right? So I'm just going to sort of discuss a bit here, sort of an example that this is another zero-var Salmonella Montevideo outbreak. Here are the time series, again, low number of cases per week. These are cases for entire Germany. You have these upper threshold, and then you see here that the spike in a particular week, you have more than that. We have to say, where can you sort of like, so far I've shown Salmonella, most of it, because that's what we started with, because we thought that's what we think that's where the potential is to gain something from this is the highest. For some diseases, these outbreak detection algorithms are not going to be so useful because the symptoms are so clear. First case is so critical. If you would see an Ebola case in Sweden, you don't need an outbreak detection system to say that you have a problem there. But there are other like foodborne diseases which can be sort of like hidden. What's noise? What's a new outbreak? Distinguishing between two of that. Or for example, like now for the COVID, you are starting to formulate all kinds of performance indicators or indicators which try to sort of should help you as detect early if you have a problem, like for example your testing capacity is running out, you are experiencing more tests, you're not really good at cluster detection. These would also be quantities you maybe can sort of formulate into such algorithms. But here we used it for gastrointestinal disease, in particular Salmonella, because that's where there was the biggest use, but it is used for all these 90 categories now. And the output of such, that's simply the output. And these are outputs that epidemiologists will get to see nowadays in a dashboard, sort of in a report, but also in a dashboard. And then you can see here the different Salmonella types. And as an example, that could be, for example, here, Salmonella typhimurium. I can check. Is that the one? I don't know. Maybe this is one of them is very often related to chicken meat, but I'm not sure it's this one. I would have to check. So here you say, okay, I'm in the week 46, which is the most recent week. YT is the number of observations I had. I had 90 was the number of observations. And here, this is something which is special for the German outbreak system. They already record if some of the cases belong together. If you have epidemiological evidence that they are connected, they ate in the same restaurant, and that's why we detected them. And then, which is also something which, for COVID, for example, would be a relevant metric, also even to indicate. So basically, this means 4 of the cases you know the explanation for why they got sick, because they were in the same restaurant. Maybe you don't know exactly what it was the contaminated product, but you know that these are belonging together. So, which is also something, a good metric to keep track of. The mu of t here is that what is the mean? That was this y bar estimate. So 120 would be expected per week. And then we have here the upper threshold limit of our prediction interval, but even you already see that the observed number is lower than the mean. Of course, there's no alarm given that week. And one thing which is a bit tricky here is, of course, these could be also undercounts, because see, the 90 is much lower than the 142. That because we are very close to this week, maybe some of these cases happening in week 46 have not been reported yet. So this is so maybe this is the reason for that. We simply said we're also going to monitor what happens in week 45, even though we are in week 46 already. So maybe the case numbers are now fuller than last week where we looked. And for example, here you would have that the Salmonella Manhattan, very low number of counts, 7, 4, 4, 3. Here we have a 3. Is usually a rather low number for the week. And actually here, the week 45, we would expect 2. And the 3 was flagged as an outbreak. Interesting enough, the week before, the 3 and the 2, same sort of upper limit and same observed number didn't cause an outbreak. Which is a bit funny. Y of t, and that should have at least here it's orange, so that means okay, so it's orange. It's not so it exceeds this threshold, but I think we have maybe one which is red, is that if it exceeds a bit further, and that depends that some of the baseline values when you did the computation here was changed a bit, but it's still a bit surprising. Maybe here is more obvious, 5 and 3, 6 and 2. I don't 100%. I think we did it red if it's several. No, sorry. I think I said it wrong. Yellow means it is an alarm, but the red one means that if it's several weeks consecutively, then we start to really flag it as an alarm. Sorry, I got that wrong. But so red means sort of like more evidence than yellow for that there is an alarm, but this would also classify it as an alarm. Okay, so this is the stuff we did, and this is something which is given to the epidemiologist once a week. And actually, I wouldn't be surprised, and I know that you have similar COVID-like indicators, but you formulate indicators in your reporting data, which should at least try to sort of help you detect if you have sort of like an increase, the second wave, stuff like that, which is also not all based on just simply cases. That's something like that is running in different public health institutions around the world. So maybe just to sort of like summarize here, these were only the Univariate. Again, each time series here was monitored by itself. Salmonella Manhattan, no connection with others. That makes maybe sense from a microbiological point of view. But there was also no geographical component in here. And we're going to look at that for the next lecture. There is an R package called Surveillance, which is implementing many of these detection algorithms, so there should be easy to use. So also for people without knowing mathematics, they can, if they have a time series and they want to know something like this, or usually they're setting up a small system because they're responsible to do something. So there's an R package developed for this, which I've been involved in. And one important message, which I think is okay to place it in the discussion, is you saw some of the algorithms are actually sort of, from a statistical point of view, say, oh, is that machine learning? I mean, this is so simple. You can do better than that. Well, yes, you can, but I mean, there's not going to be a perfect system. I mean, what does it actually mean to have an alarm? Is it justified? What is causing it? I mean, there are all kinds of artifacts in the data that one federal state or one county is simply reporting many cases in 1 week because they didn't have the capacity to do it for a number of weeks. One explanation, right? So it's very important to realize that creating such detection systems really interdisciplinary activity. You need to sort of collaborate with people who come from the epidemiology, who understand the reporting system. If you're gonna sort of like, people want to use this, sort of like, you need to ask, what do you need? What's the question? What do you need? What could be helpful? Not sort of like, here's the coolest algorithm. It uses a neural network, and I use a big cluster up in Karuna to sort of compute all of it, and now here are all your alarms, and see you tomorrow. That's not gonna work. I mean, it's gonna be sort of like a dialogue. What do you need in your report, and so on. And sometimes the simple things are easier because they still grasp. So for example, something like the mean, we said the mean is not relevant. It's the variability which is relevant, and thus the upper threshold, but they still wanted the mean because in the table, because they want to say, I want to assess it. And of course, something which we then created for them is also that if you have such an outbreak, you click on this and then you get the time series, so they can look at it, and then they can go into the dynamic component and say, we want to change. If we're just going to look at this particular age group, how does it look? Is it maybe all even more of sort of more females than males? That's the stuff that would be typical in such an outbreak detection, sort of like outbreak investigation for contaminated food products. That would be the sort of things you look for. Okay, and that's always a one question. If you set up a system, does it work? Well, it does work. We can say that. I mean, it's the question is what's the added value? It's not like it's going to detect several more outbreaks or many more outbreaks than before, because there's still somebody who has to sort of like keep track of it and monitor it and decide if this is important enough to do something with it, and there's only limited time to do so. So of course. It gives, and this is the important message, it gives a safety feature that you monitor these diseases. If you don't have a lot of time to look at them for various reasons, then there's still an automatic system, at least sort of making sure you don't miss anything important. And here there's also a publication about a cryptosporidosis outbreak, which is due to flooding in Germany, which was concurrently detected by the system and by the local authorities. But still, it was sort of like not detected by eyeballing because it was vacation time, for example. So this is where you sort of like have stuff like this, and of course you can have, and we will look a bit more about that. On that, you can also find sort of like outbreaks which the local authorities won't see because they are sort of like scattered around the country. This is also where this is useful. Yeah. Okay, so that was what I had to say. This was less mathematical, less statistical, but it gives you sort of like, if you move into the data science and that things need to be done. This is important work, because people have been publishing all kinds of sort of like clever algorithms on what to do and how to do the outbreak detection, but the epidemiologists actually at some point say this is not helpful for us, because there was sort of all these alarms that generate a lot of work for us, and please turn the system off. So you need to sort of like really now you need to start to worry about sort of like, how do you actually do something useful and build it up from sort of like iteratively in smaller steps, but it's useful at the time. And that's even if you do statistical consultancy or you use such algorithmic approaches to problems like in infectious diseases, then I think this is a very important approach if you want to do something which people use. You can be interested in things for purely theoretical reasons, that's also fine, but then usually you work in the math department. There you don't need to, but you can. And I think sort of the nice thing is if you have the combination that you know your statistical methods, but you still can get messages across. What does it mean, and how can this be useful for people? I think that's the when it's fun to work with this. And these shall be the closing words for lecture 9. We'll have a live session where we can discuss all of this. I hope you have some questions to think of. I didn't prepare any exercise questions for this one here, because I don't think you will actually have any motivation to look at them. But maybe I can add one thing. It will be more for the exam than it will be for the project work, I would expect. So maybe we can do some of the small calculation that I show. Maybe this can be added. But for now, we can discuss some of it for the live lecture. And see you there. Goodbye.